Welcome and hello. This is a video tutorial in HEC HMS, and in this lesson, I'm going to be discussing long-wave radiation as part of a meteorological model. All right, what I have on the screen here is my HMS. Down here in the components editor for a meteorological model is long-wave as one of my methods. And what we'll be talking about again is these options here from FAO 56 all the way down through Stefan-Boltzmann method. All right, just taking a quick step back here. What I have is my watershed that's sketched out. There's two basins, basin one with a couple subbasins, basin two, a couple other subbasins, and then I've created the meteorological model. Also in this model, if I click the basin tab down here in the components editor, I have selected yes for both basin one and basin two to be connected to this meteorological model. Long-wave radiation represents radiant energy that's given off by bodies. This includes energy radiated by the land surface upwards towards the atmosphere, as well as energy radiated from the atmosphere downward towards the land surface. Long-wave radiation plays a crucial role in hydrology and by influencing various processes such as evaporation, soil and water temperatures, snow melt, ice melt, among other things. For this reason, long-wave radiation is only necessary when energy balance methods are selected for evapotranspiration and also for snowmelt at the subbasin level. Let's go ahead and get started with our long-wave radiation discussion. First up is FAO 56. This method calculates long-wave radiation based on the day of the year and the angle that the sun is in the sky at each time interval of the simulation, using the georeferenced coordinates of the subbasin. All right, so let's go ahead and select FAO 56 here in the Watershed Explorer. And if you notice, the subbasins are also listed down here, which means if we expand, we will see that FAO 56 now has parameters up at the model level as well as the subbasin level. Up at the model level, we're expected to provide the median degrees. I'm just going to type in a value here. This value must equal the central meridian of the time zone of the watershed. The user can provide this value in decimal degrees, like I've done here, or in degree minute seconds, which is available to you by going up to Tools, Program Settings, and then in this first General tab, you can switch that latitude longitude setting to degrees minutes seconds right here, and then click OK. But I'm not going to do that. A parameter value we need to provide at the subbasin level is the elevation. So elevation is the only method, and then we'll just go ahead and type in an elevation there. This elevation is used to calculate the long-wave radiation from the clear sky radiation. The user's manual also mentions that when we're using FAO 56, that we also need to set the temperature method and the wind speed method here in the meteorological model. So we have temperature here and wind speed here, because this method calculates the vapor pressure as a humidity correction. The next method for long-wave radiation is called gridded long-wave. This is the most common method for radiation. It's used because gridded long-wave radiation estimates can be calculated or produced as external data sets and then included into HMS for the simulation. To do that, we'll go ahead and select the Components menu. We'll go to Grid Data Manager here. And then for the type, we're going to select Radiation Grid Sets. All right, and then we'll click New. Go ahead and type in or paste in a name and then click Create. There is the long-wave radiation grid set I just created. And then if I select Gridded Long-Wave here, the grid name is the parameter we need to define. It's the only required parameter, and we can make that selection right here. To define the actual values within that gridded data set, we can expand the grid data and radiation grid set directories in this Watershed Explorer, select on the data set, and then provide a link to the file name and the path name of the DSS file where that data is saved. Okay, the next method is going to be interpolated long wave. So if we select interpolated long wave, this method allows the user to interpolate long wave radiation grid based on other point radiation grid data nearby, based on its latitude, longitude. So what we're going to do here is create a few different time series data sets for radiation gauges with latitude and longitude values. And then after that, I'll explain the different interpolation methods. So let's go up to Components and then this is going to be time series data manager. The type is going to be radiation gauges. So fifth one down, new. Okay. And then I'm just going to type or paste in some names. There's A. And then let's go with the second one. That'll be B. And then let's just do one more. That'll be C. Okay. You get the idea. Let's expand our time series data set and then radiation gauges. So we have A, B, and C right here. On the first tab for the components editor, this is where we define if it's manual entry or a DSS file. For remember, time series data set. Our units are right here. The time interval is right here. And then what's also important in this situation is the latitude degrees and longitude degrees. Of course, we can do degree, minute, second as well, but right now it's just set to decimal degree. The actual location is important because the interpolation methods all require that distance from the target cell of interest to the locations or the distances from these radiation gauges. Once that's done, we can expand to click on the time window. This is the first day of the year 2000. This is just default time window, but go ahead and change these values to whatever start and end date time that you're using for your simulation and you have radiation gauge data for. And then once that's done, you can either type in or paste in the actual radiation values right here in the table. As before, if you have DSS records to represent that data, you can go ahead and select DSS and then provide a file name and path name. Going back to the meteorological model, we click on interpolation. We have a few different interpolation methods to select: inverse distance squared, nearest neighbor, and bilinear. So this is a required field. If we go with inverse distance, this basically says that the closer the gauge to the target cell, the more influence that that gauge data has in the interpolation process. And also the inverse distance squared is similar, but it's even more influential because the distance is squared. It's 1 over the distance squared. So the smaller the denominator, i.e. the closer the gauge, the more influential that one gauge's value has in the interpolation process. The third method is nearest neighbor, and this basically means it just assigns the exact same value to the target cell as the nearest gauge. And then the last one is bilinear. This is probably the most complicated. What this does is it creates a triangulated network based on the location of all the radiation gauges, based on that latitude, longitude that we provided. And then whichever triangle our cell or our coordinates of interest falls within, then there's a basically a 3-point linear interpolation process to determine that calculated radiation value. All right, so those are the different options for interpolation method. Further below, we have this table. It's called the radius of influence. And what it does is it sets a limit, a maximum distance on interpolation. So for instance, if we had a gauge that we knew was not reliable past a certain distance or something, we could just type that in and say 20 miles for this gauge and maybe 30 miles for that gauge. This is sort of up to the discretion of the modeler. And again, this is not required. It's just optional. Okay, let's go back to the next method. So for Longwave, that is Saddleloon. Saddleloon does not have any basin-wide parameters or model-wide parameters for all the basins, but if you expand on the sub-basin itself, we see Saddleloon here and Saddleloon and so on. When using the Saddleloon method for long-wave radiation, we need to provide the emissivity coefficient and the temperature coefficient, and this is in Kelvin. The default values you're seeing on the screen here is 1.08 and 2016, and I'm just going to leave those values as they are. When using Saddleloon method, the user also needs to provide a method in the meteorological model for the temperature, as well as the wind speed, as well as the dew point. So it's basically going to be using some of the output calculations from these other methods to calculate that long wave radiation. The next long wave radiation method is the specified pyrgeograph. And this method is showing up as individual subbasin where I select the subbasin and I select the gauge. A pyrgeometer is an instrument that can measure downwelling long wave radiation, and that may be included in certain first order weather observation stations. So this is not a very common instrument, but it does exist and it measures that radiation directly. So what we're going to do is for each subbasin in this table is assign it a specific radiation gauge. It could be one of the gauges that we've already created, or it could be a new gauge altogether. Again, this is a time series data set. and it would be defined the same way any other time series data set is defined. But just to be complete, I thought it'd be appropriate to actually walk through that and say time series data set, and then the data type is going to be radiation grid sets right there, and then click new, give it a name. I'll just say this is good for all, and then select all. The last method of long wave radiation is going to be Stefan-Boltzmann. So if I select that, I'll go ahead and select Stefan-Boltzmann icon in the Watershed Explorer. And what I'm seeing here as parameters is my atmospheric emissivity method and the saturation vapor pressure method. Now, we only have one choice for the emissivity, so that will be my choice. And then for vapor pressure, we have two different options here. The user's manual doesn't go into detail about what these mean, and to be honest, I don't either. So in a later lesson, I will provide you that information if I find out. When using Stefan-Boltzmann method, you also need to provide the temperature gauge right here, as well as the relative humidity, because this method estimates the long wave radiation using temperature and relative humidity. Well, that's it for this lesson on long wave radiation. In HEC HMS, we talked about the different methods and then the different parameters briefly and some of the requirements and how to fill them out. Again, this is long wave radiation as part of a meteorological model in HEC HMS.